So we're going to switch back to OMEC and SP Gateway. And so this is a work that I'm collaborating with Sai on this. And this is the work that we're trying to revise. Our main focus is to revise the user plane SP Gateway with a new framework, which is much more developer friendly and operator friendly as well. So for this, we are all familiar with this diagram. This was actually just discussed in the tutorial on the first day as well. So I'll just skip through this slide. What I will be focusing on as far as this slide is concerned is that in the default version of SP Gateway that is available on the OMEC GitHub side, the S gateway and P gateways are co-located. The user plane are both co-located, and the control plane for S gateway and P gateway are also co-located on the same core. So yeah, so this is a default setup. Now in the following slides, we're going to do a deep dive on the OMEC user plane SP gateway, and we're going to discuss why the current architecture is kind of fixed, and what we're trying to achieve in this talk is whether we can make this more flexible. One motivating example as to why this looks a bit too fixed is that if you look at the source code of SP Gateway user plane, we're going to quickly realize that we need 4 CPUs to actually run the SP Gateway user plane. One core is actually used to handle uplink traffic. The other core is used to handle the downlink traffic. And then there are 2 extra cores that the current SP Gateway user plane is using. One to handle CP communication coming from SP Gateway Cs, and the other core is actually used to handle kernel communication, from where we can get ARP updates and route updates. So the question we're trying to ask is the current model a bit too over allocating in terms of computer resources? And do we need separate CPUs for these 2 functionalities? This can become an extremely critical question when we try to scale out this user plane into more and more instances. This actually means that we are actually investing 4 CPUs every time we install separate instance of SP Gateway user plane. That's why this design looks a bit more too fixed for us, and we want to make this thing a bit more flexible, as in reduce the number of cores at runtime dynamically. The other issue with the current release is that the CPU, the configuration of any component of SP Gateway user plane needs at least a process restart or recompilation of the code, or in the worst case, the rewriting of the code itself. One example can be that the current implementation that is out there is adjusted so that it can have 2 interfaces, S1U and SGI. Some operators would rather want to have only single interface mode as well. In that case, you will need to have a code rewrite. Same goes for multiple interfaces, more than 2 interfaces as well. The current version only provides run to completion mode. There's no flexibility with regard to changing the model itself. And moreover, if we want to do some fine-grained CPU scheduling for certain sub-modules in the SP Gateway user plane pipeline, it's very difficult to do that. Probably one has to hack into the source code and rewrite some part of it. So with all this, let me introduce the ongoing effort that we're doing. We're trying to port the SP Gateway user plane on a data plane programmable platform that provides this intrinsic support by default. So we can just utilize or exploit these features by just a one-line command. So we decided to pick up BESS, which stands for Berkeley Extensible Software Switch, which has these useful features. It has a completely clean slate internal architecture with NFV in mind. It's highly flexible and customizable. So the idea is that the SP Gateway user plane can be broken down into submodules, and these submodules can be linked up in a form of a chain representing a directed acyclic graph in a BESS application. You can run in each submodule can run an arbitrary code, and each module is extensible and optimizable, and we can hack into the modules independently. As in, we won't really care what other modules are linked up. We can only focus on the module that we want to optimize, and it's very easy and developer friendly in that way. I'll explain that in the following slides, what I'm trying to say. The best daemon, once it hosts the the SP gateway user space best application, can easily be controlled using a controller. Visually, this is how a best application would look like. We only would want to run the best daemon one time at process start. We don't want and we don't need a process restart for any configuration update. It runs completely in user space, and by default, Best Daemon provides a number of I/O driver support such as DPDK, IGBIO, AF packet, AFXTP, as well as its legacy driver support is also there. The idea is that the SP Gateway user plane modules will come in the brown boxes, and these modules can then be controlled externally via some Python scripts. And those scripts are called controllers. One example controller can be talking to the control plane SP gateway and interpreting the command, and then sending these commands to individual modules using gRPC. So these controllers can either be written in Python, like I said, or in Go scripting language. So for example, the net controller in this example figure can be talking to a UE session management module. And then on the fly, new policies or new rules can be updated in that module individually. So controller won't really care what's written before this module or what's coming after this module. Similarly, the second module, which is the host controller, can talk to the router module, and the host controller can be talking to the kernel itself, and it will maybe using netlink sockets to get route updates and ARP updates, and then it can then use gRPC to communicate to the router module to update the traffic directions. So the packets can come through one of the driver modules in batches, and the module individually will process these packets and pass them to the next module in line in batches again. So in more simplistic terms, I've actually created an abridged form of the uplink direction of the SP Gateway user plane pipeline. So most of the modules in BESS are built in, as in the BESS authors have already provided those modules. We are just using it with just a few lines of code. And the cool thing about using BESS is that we can pin down the fast path of the pipeline to an individual core at runtime. We don't need a reboot or a code rewrite. And the slow path, which can be used to redirect ARP traffic or ping traffic to the host gateway itself, it can be pinned to a different core, and the packets, ARP packets or ping packets, can then be redirected using another sequence of modules that is talking to the kernel. So this VDEV is a form of a ETH VDEV kind of a module. The filter is also a built-in BESS module. It will parse the incoming packets based on the IP headers and the GTP port numbers. If the packet is encapsulated, the batch of packets are going to go this way. If it is, let's suppose, an ICMP or an ARP packet, this filter is going to redirect traffic over here. We can have a bunch of other features that we can set dynamically. We can prioritize using a Python scripting command to any of the modules, and we can also do rate limiting for certain subset of modules as well. For example, for the slow path, we can restrict 10% less CPU, 10% up to 10% CPU cycles, so that the remaining 90% cycles are invested on the fast path modules. Same goes for as far as the bit rate is also concerned. We can also rate limit using bit per second values. Okay, so why is moving the OMEC SP Gateway user plane to a good idea? I've already summarized some of the key features that BESS is providing by default. The overall architecture becomes much more modular with best version of SP Gateway user plane. A developer only has to concentrate on the core business logic and not worry about infrastructure development. The average source lines of code for each such module that we have written ourselves. So in this above example, GTB decap was not a built-in module. We had to write it from scratch. So modules such as these are only span anywhere between 200 to 500 lines of code. So this results in an overall thin stack, which makes the entire stack very developer friendly, very easy to understand. The controllers, once as I mentioned, can be written in Python or Go language or even C++. And we can actually dynamically on the run change the CPU pinnings of the modules. We can also add or remove modules without process restart. Workers. I've already mentioned about the worker disabling and enabling workers at runtime. That is also very easy to do in BESS. And we can convert the overall runtime model from run to completion to pipeline while the process is running. Our new framework is also operator friendly. The default version of the OMEC version of the SP Gateway user plane uses KNI, which is not really by default, so which is not really cloud native friendly. In our new version, we are actually using VH pair and AF packet interface to talk to the kernel, which then makes the entire setup cloud native friendly. And we have BESS provides a lot of monitoring tools, such as TCP dump and a web-based monitoring interface as well, which I'm going to show you in the demo. And the entire talk will become much more easier to understand once I actually show you an actual demonstration. So, can you see my screen? Okay, let me just increase the font size. Okay. Okay. And changing for black and white. Okay, let me just change that. Colors. Okay. Foreground. I think I can make it. Okay, I think this is visible. Okay, I think we can. So let me just show you how best version of SP Gateway user plane looks like. We have the entire setup Dockerized. So with this command, one can actually set up SP Gateway user plane on containers. So this actually sets up 4 containers, and this command actually sets up the SP Gateway user plane pipeline. It will take a few seconds because it's also creating UE sessions, because we're going to use IL traffic gen to blast data plane traffic. Okay, so if I were to run Docker PS, you're going to see that there are 4 containers that are created. The last one is actually the best daemon itself, which has the running pipeline. And the route controller is running on a separate container, which is a Python script that is talking to the kernel and which is listening for neighbor updates and route control updates. We have another container that is talking to this control plane, and the last container is actually the visualization monitoring tool, which I'm going to discuss, which I'm going to show you shortly. Okay. So the first thing that I wanted to show you is the best visualization graph, which actually talks to the best daemon and sees which modules are linked up. So this starting point shows you the start of the uplink pipeline of SP gateway, and this guy SGI fastpath is showing you the starting point of the downlink pipeline. It goes through PPF filters that I discussed in the slides before, and then it's going through the normal pipeline all the way to the SGI and S1U port out modules. So these are the packets are being passed from one module to the other in batch format. So if I were to run an IL traffic gen, excuse me. Actually, so this is not really that important. This will take more time. So when I start generating traffic, we're going to see some activity on these graphs. So you can see that okay, this is a bit slow. So you can see that these numbers are now being filled up with some packet rate, and we can actually also see the total number of packets that every module is seeing. If I can only scroll up, yeah, okay. So you can see that the packets are coming from S1U interface, represented by this module, and you can see a running count as we are blasting packets through IO traffic gen. So this is a very cool debugging or monitoring tool that BEST provides, which one can use if we were to start using the BEST version of SP Gateway user plane. The other cool thing that I wanted to show you is the TCP dump approach feature. So we can actually run TCP dump on individual modules that we want to monitor. So let's suppose if we were to start monitoring S1U fast BPF filter, and you can immediately see that I believe this interface is actually connected to a switch, so we're getting background traffic right now. And we start blasting packets again, and you can see that now some UDP packets are also visible. So during debugging, this tool can be very useful, as in if some rules are invalid, have been inserted by some mistake, you can get inside BEST Daemon using BEST controller. This is a BEST controller shell, another shell written in Python. One can log into the pipeline shell, and then you run TCP dump to see which packets are going where. Okay, let me just go back to the slides. So this is basically, so the next slide, okay. So this is just a summary of what I was showing you on the web interface. It's just showing that the starting module, I think the fonts are not visible, but I could just tell you verbally, the interface module that is accepting traffic is based on TPDK poll mode driver. Then we have pinned that module to CPU 0. We are rate limiting the slow path to this metric. And finally, we are also the modules can be controlled using a controller which has these sets of function calls. Performance-wise, we are actually matching the GitHub version of OMEC NGIC, and we were testing this thing on a Skylake machine. The good thing is that in our setup we were using less number of CPUs because we were using rate limiting as far as CPU cycles are concerned for the slow path. So with those intelligent scheduling policies, we are saving CPUs. So what's done? So we have actually implemented NCAP, DCAP modules. We have completed interfacing with CP. So the most important thing is that our SP Gateway user plane is the only thing that we have touched. All other components of the VNFs that are out there in the OMEC are compatible with our user plane. So no other change is needed. We just need to plug in our SP Gateway user plane, and this will work. So we have already implemented NCAP DCAP module, IP reassembly, fragmentation, echo response. What we're doing right now is working on charging and metering. We have done most of our implementation, but we still haven't released in open source yet. We're talking to the OMEC guys to just put it in a separate repo, whatever we have contributed so far. And this is just a summary of the differences between the SP Gateway best version and the OMEC version. With this, I would like to end my talk, and if you have any questions, please, you can ask me.
Hey, I have two questions.
Yes.
First one, BESS, BESS, and eBPF. Would you mind expanding a little bit on if they're related at all? So I know eBPF is like Evolved Berkeley Packet Filter.
I'm sorry, I couldn't hear you. Can you say it again?
Sorry. So BESS and eBPF, are they interrelated whatsoever, or are they very different?
No, eBPF is BESS is a full framework. Have you heard of Click Modular Router or some? Click Modular Router is the best example to compare BESS with. eBPF is kind of like a filter, a sort of a compiled code which can then be used to check what are the classify packets. But BESS is providing a full runtime engine through which you can actually process all the packets and then send it out as well to a different interface. I'm not really sure how you are comparing these two, eBPF and BESS.
Oh, I was purely wondering because Berkeley Packet Filter, it just sounded similar.
No.
Yeah.
No. BESS, no. That's two completely different things.
Okay, thank you very much.
Any other questions? Okay, no more questions.
Okay.
Let's thank you, Asim, again for
right.
the great work here.
Okay. All right.
And
thanks.